Hi, in this video I will explain how to determine the relationship between two compounds. Since it is usually difficult to determine whether two compounds are mirror images or not, especially if the structures have been changed too much, then the best way to determine the relationship is by finding the absolute configurations and then comparing them. For example, in this case here, starting with the molecule on the left side, this is group number 1, this is group number 2, this is number 3, and this is number 4. So we're moving 1, 2, 3, we're moving anti-clockwise, and this is S. For the second molecule, this is 1, 2, 3, and 4. 1, 2, 3, we're moving clockwise, and this R. Since those two molecules have opposite absolute configurations, then the relationship between them is enantiomers. And of course, pay attention that if you have only one chiral center, it's impossible to have the relationship as diastereomers. So diastereomers exist only if the compounds have two or more chiral centers. So in this case here, both possibilities are valid, either enantiomers, diastereomers, or even identical. Again, the first method is try to determine the absolute configuration. At this chiral center here, this is 1, this is 2, and this is 3, and of course this is a hydrogen, which is number 4 in the back. 1, 2, 3, we're moving anti-clockwise, so this is S. For this chiral center, this is 1, this side is number 2, this side is number 3, and there is a hydrogen here, and it's number 4. 1, 2, 3, we are moving clockwise, so this is R. Now there's no need to waste our time here by doing the absolute configurations, because the Cl is still the same, so this is R. And what they did here is that they inverted the wedged bond into a dash bond, which means that for sure the stereochemistry will be changed. So instead of being S, it will be R. So now we have RS versus RR. So this is partial inversion. We didn't completely invert the stereochemistry. We have partial inversion. So one of the chiral centers is inverted, the other one is not. Since they are partial inversion, or basically they are partially opposite, then in this case the relationship between these two compounds is diastereomers. The other method which can be used in this case here is the following. If they didn't rotate the structure, so the carbonyl is still on the right side, this is still on the right side, OH, and to the left of OH cell. So basically there is no inversion of the structure. Then just compare the dashes and wedges and see here, the Cl is wedge, Cl is wedge, so no change. OH is wedge, OH is dash. This is inverted. So again, we have partial. These are partially opposite, and since they are partially opposite, again they are diastereomers. However, when you apply this method, make sure that the structure is not inverted, and by inverted I mean the following. They may give you another structure which, for example, looks like this. In this case, you have to pay attention So for example, you cannot just say that this is wedge and this is wedge, this is wedge, and this is wedge, so this is the same. In fact, those are not the same. They are actually enantiomers. So pay attention that the structure is not inverted or reversed or rotated. Now let's move on to Fisher projection. Again, in Fisher projections, if you are able to just figure out whether the groups switched positions, then you can use this method. Otherwise, if you have so many changes, you have to use the R and S method. So if I'm using the R and S method, this is number 1, this is number 2, this is 3, and this is 4. So 1, 2, 3, we are moving anti-clockwise, so this is S. 1, number 2 will be here, this is number 3, and this is number 4. Number 4 is in the back. So 1, 2, 3, I'm moving anti-clockwise, so this is SS. For the second molecule, again, if you pay attention, OH left side, H top, Cl right side, so this doesn't change, so that's why this is again S. Let's check the bottom carbon. This is 1, this is 2, 3, and 4. 1, 2, 3, we are moving clockwise, so this is R. However, pay attention, 4 is not at a vertical position, and that's why R should be S. So the first molecule is SS, the second molecule is SS, which means that those two compounds are identical, since we have the same absolute configuration. Again, in this case here, if you use the RNF method, this is 1, this is 2, 3, and 4. 1, 2, 3, we are moving anti-clockwise, so this is S. But again, pay attention, 4 is not at the vertical position, so this is R. For the bottom chiral center, this is 1, the top carbon will be number 2, this is 3, and this is 4. 1, 2, 3, we're moving anti-clockwise, so this is S, but again, 4 is not on the back, so, or at the vertical position, so this is RR. For the second molecule, you have to determine R and S, and again, if you just do them, this is 1, 2, 3, so this is R, and it becomes S. You can do that on your own, and then this is 1, 2, 3, and this is S. So the first molecule is RR, the second molecule is SS. Those are completely opposite to each other, which means that the relationship between these two compounds is that they are enantiomers. Always, usually the absolute configuration method of determining relationships takes some time. However, its results are guaranteed that it gives you the correct answer. Sometimes if you have to look at which bonds were inverted and which ones are not, sometimes it's difficult and it may look confusing to some of the students. For example, in this case here, if I want to use the inversion method, I would say that those two changed their positions, which means that for sure in this chiral center, this is opposite here. And then in the bottom carbon, I can see that H and Br also changed their positions. So again, we have one change here. So again, this is opposite. Since both are opposite, those are enantiomers. However, you have to pay attention because sometimes they may do so many changes. So for example, in this case here, if I'm using the inversion or whatever, the change of position method, those are the same, which means that it's impossible for this compound to be an enantiomer. So these are either diastereomers or identical. Now I have to pay attention that first of all, we switched the CH3 and OH positions, and also we switched the hydrogen position. So basically we did two changes. As if we moved the CH3 to here and OH, let's say to here. And then later on, I switched the OH and hydrogen. So we have two changes. Two changes are nothing, which means that this is again the same, and that's why this is identical. So if you want to use the change of position method, you have to pay attention that one change will invert the absolute configuration, whereas two changes will keep it the same. And that's why in this case here I said it's the same, because we did two changes. In order to be able to transform this chiral center into this form, you have to do two changes, no matter what those two changes are, but you need two changes. One change cannot take you from the first chiral center to the second chiral center. Since you need two changes, then this means that the stereochemistry is the same. If you need one change, then it is inverted, okay? And this also applies here, okay? So as I said before, This is no change, so this is the same. This is a change here, so this is opposite. Since one is the same, the other one is opposite, the relationship is diastereomers. However, pay attention, as I said before, if they inverted the structure, so if I did an inversion of the structure, then the inversion of the structure, or not inversion, it's basically drawing it in the other way around, this is considered was one change. And then, so by just, since this structure is just drawn in a different way, this is considered as one change, which means that any other change will keep the stereochemistry as it is. So in this case here, so OH is still wedge, this is wedge, so we still have one change at the first chiral center, and then for the second chiral center, this is Cl. For the second chiral center, again, this is wedge, so we didn't change anything. So we just have one change, which is the initial one, and that's why, since we have only one change at each chiral center, this means that this compound and this compound are enantiomers. So again, if you get confused with the change method, and it's considered as a challenging method, then you can just use the absolute configuration method to determine the relationship between these two compounds. Or you can use both and then double check your answers by using one of them and then checking with the other one.